Okay, so this is session D, DNS of turbulent combustion, and I'm Venkatraman, I'm the chair for the session. So the first talk is from Evatt Hawks at University of New South Wales. Evatt is very well known in the combustion field. He's a regular participant in the combustion symposium and the TNF workshops. He got his PhD from University of Cambridge in 2002, I think working with Stuart Kant.
Stuart, yeah.
And then he was a postdoctoral fellow at Combustion Research Facility at Sandia. He was working with Jackie Chen, doing DNS calculations, and he's done a number of them. They're all very well-known flames actually by now. After that, he went to University of New South Wales, where he's an Australian Research Council Future Fellow, and currently associate professor at the university. His work is mainly on engine emissions and alternative fueled engines. He does both experiments and simulations, and I think today is going to talk about DNS.
Thanks, Venkat. A real pleasure to be here today and have the opportunity to talk about some of our DNS of lifted and premixed flames. I'd like to first acknowledge the guys who actually did the work. Haiyu Wang is a postdoc at UNSW. He did the work on premixed flames that I'll talk about. Shao Karami is a PhD student, currently looking for a job, by the way, if anyone's interested in employing postdocs. He did all the work on the lifted flames, assisted by Mohsen Tali, who was a postdoc at UNSW and is now faculty at University of Melbourne. So we're sort of new on the combustion scene here at UNSW, so I thought I'd maybe just give an idea of where we are. So we're down under, pretty far from everywhere. We're in the southeast coast of Australia, in the city of Sydney. As you can see, that's our little campus there. It's pretty central in Sydney, and as you can see, we're quite a lot more squeezed for space than you are out here at KAUST. It's a very vertical campus, and it's very sort of busy sort of year-round. We also, as you can see, we're very close to the beach, which is fantastic. All you have to do is make really sure that you do not hire any PhD students who are keen surfers. In terms of the UNSW, we're a fairly new university, but we're quite strong in several areas, notably in engineering. We're actually now the largest engineering faculty in Australia, about 50% larger than the next largest faculty. And we're sort of, I guess I sort of regard us as the other place in combustion in Sydney. So our group is 4 of us now. It started with a group size of 1 in 2007. When I joined after my postdoc at Sandia. So I mainly work in modelling. I work in 2 areas now. I work mainly in combustion, about 75% in combustion, but also the rest of my time is devoted to solar energy research. So I guess I'm kind of 25% renewable in that sense. My combustion modelling work is mainly in DNS, which I'll talk about today, but we also work with LES and also on the very applied end where we do actual RAN simulations of engines and so on. On the experimental side, we have Sean Cook, who's an engine experimentalist. He has a couple of optically accessible research engines, one gasoline and one diesel. We have Sean Chan, who works more on fundamental flame diagnostics, temperature measurements in sooty flames and so on. And on the solar energy side, we have Rob Taylor. It's concentrated solar thermal energy that he's interested in, and he's also developed some very nice facilities, including some solar furnaces, which we're investigating some solar-driven chemical reactions in. The overall size of the group, so there's the 4 academics, we've got a few postdocs and about 30 PhD students working across these different areas. So in terms of motivations for this talk, I think it's good to make it personal, and I'll do that here by just showing you where I grew up. This is a rainfall map actually of Australia. I grew up here in Perth, which is on the southwest. And as you can see, there's this little kind of green patch there where there's some rainfall. And if you know anything about Australia, the rest of Australia here is basically a desert. So we're really right on the edge of the desert area. And so that makes Perth, in fact, a region of the planet which is very susceptible to climate change. And you can actually see that here on this rainfall map of rainfall into Perth dams over time. So I was actually born... Oh, this isn't working. I don't know why. Okay. I was born here in 1972 on a sort of a bush block, a little bit on the outskirts of Perth. About half of the block was kind of a wetlands, sort of a swampy area. The other half was, sort of on a hill and dry land. The property was sort of marsh-like, and there's a whole lot of frogs. And at night time, these frogs would be really going for it, and the noise would be really deafening. Sort of about 10 years later, the creek sort of only flowed intermittently after storms and developed a bit of sort of an algal bloom, and there were noticeably fewer frogs. And now sort of, by the sort of mid-2000s, that whole swamp area is now completely dry. So all of the swamp vegetation is dead, all of the frogs are gone, and even some of the large trees on the property have died. So that's a really pretty big change to happen over only 40 years. where you can go from a region that was wetlands and now is a completely dry area. And of course, this is an extreme example, but this is happening globally, and we need to do something about it. So, what can we do as combustion scientists and engineers? Well, we need to obviously transition away as much as possible from high CO2 emitting devices, and I think gas turbines have a very important role to play in that transition. Of course, as we know, there's simply no other option in aviation, so we just simply need to stick with those for the time being. But they also have important roles to play in stationary electricity generation. I expect that in the future in electricity there will be very high penetration renewable energy. It's coming a lot faster than probably most of you know about. And then we'll need these sort of energy sources that can ramp up very quickly, such as a gas turbine, to complement the intermittent renewables in a cost-effective way. We also Anthony Dean pointed out this very nicely, that they're very efficient, about 60% currently, which leads to about half of the CO2 emissions compared with a coal energy plant for unit energy delivered. And they're also very fuel flexible, which will be increasingly important in the future, and also possibly in a very long-term future where we may be developing fuels directly from solar energy. There are a lot of technical challenges that need to be sort of solved to make the gas turbine more efficient and cleaner. And other people, there's been some very nice talks on gas turbines already in this conference. Other people have outlined these probably better than I can. But there are emissions trade-offs between NOx and CO and unread hydrocarbons. There are issues of stability. There's blow-off stability as well as thermoacoustic instability. And I already mentioned this, but we need to have fuel-flexible turbines. And these are all technical issues in which improved fundamental understanding of gas turbine combustion can help. So where can DNS potentially play a role here? So as you know, DNS resolves all of the continuum scales, reasonably well at least, of the problem, i.e. no turbulence model needed. And so the advantage of that is that you have the full data available. So you have the chance to understand fundamentals, and you also have a very good chance to develop and validate sort of engineering models of combustion in a setting in which the submodels are all known quantities, like the chemical kinetic submodels and so on. Of course, there's disadvantages. The big one is that we just don't have enough computing power to get to conditions of practical interest. The worst manifestation of that is in the problems with ranges of scales. So really high Reynolds number for DNS isn't possible. At the moment we can push Reynolds numbers up to sort of, turbulence Reynolds numbers of up to sort of 100 maybe to 1,000, while we're talking, practical gas turbine, we're talking at least sort of 100,000. So we've got a long way to go. It's sort of maybe 1 million to 1 billion times more expensive computation. And as John mentioned, we just probably won't get there ever, at least with current sort of silicon-based computer hardware. We have issues, obviously, with limitations on other submodels, inaccuracies of those models, which might lead to incorrect conclusions. And also, the thing that John mentioned, we then have the full data available. So we actually have, absolutely everything, and we're faced with a big challenge of what the hell we're going to do with this, in order to distill some conclusions that, you can write in your conclusion sentence in a combustion and flame paper. And that's really a difficult job. So over time, we've seen a good development, I think, of the DNS capabilities, which has pretty much followed the development of supercomputing capabilities, which this shows. This is a logarithmic scale here of the floating point operation per seconds versus time. We saw the very first DNS come out in the early 90s. I think Thierry Poinceau was the one who really spearheaded that. These were sort of one-step chemistry models of sort of weakly wrinkled flames in boxes. Then sort of mid-90s, the field diverged a little bit, and we had some people, for example, Jackie Chen's group, doing 2D with detailed chemistry, and other people doing 3D with one-step chemistry. Sort of mid-2000s, it started to become possible to do 3D and some multi-step chemistry. We started to see the very first lab-scale flames happening. This is one of John Bell's early V-flame case. When was that? 2002? Something like that, yeah. So we started then to see more complex configurations, and now we're finally in this very interesting era, I think, where it's become possible, with admittedly very large allocations of computing time, but it's become possible to overlap with typical experimental jet flame cases that have been done, for example, in the TNF workshop over a long time. So just outline of the talk. I've done the introduction. I'll just briefly describe our numerical methods. Then I'll talk about two topics where we've applied them. One is a lifted flame case, and the other one is a high Karlovitz number premixed flame case. So we've used the code S3D, developed it at Sandia Labs over basically since the mid-90s. The approach to this algorithm, it's a little bit different from John's. It's a very, very simple algorithm. I think John actually called it a hello world code, which is actually pretty accurate, I think. But the advantage of this is that it's very easy to port, and we can actually make it scale extremely well. So we've sort of been a case in point for using these large resources. The time integration is fully explicit, which notably doesn't require any all-to-all communication. Spatial differentiation, again, is also fully explicit with no all-to-all, only nearest neighbour communication needed. We also take a lot of effort to minimise the sort of amount of time waiting in computation. We do that with NPI rank placement, so according to the memory architecture, as well as interleaving the computation and communication. And we have the advantage, like all combustion people, we have this large point workload that doesn't require any communication at all in the chemical reaction rates. So this is just to demonstrate how well it does scale. This is a strong scaling plot on the Cray XC40, which I believe is the 100-ton machine that you guys are going to get. Ours isn't quite 100 tonne, it's probably only 10 tonne-ish. That's what we can afford in Australia, but you can see that this is like perfect scaling is a flat line, and you can see that we do achieve that going up to the size of that particular machine. So I'm a bit jealous of this new hardware that you're getting. It's pretty impressive. Yours will be like 8 times bigger than that, I think. Okay, so moving on to the technical part of the talk, I first want to talk about some work we did on lifted flames. Just very briefly going over the motivations. These occur in gas turbines, industrial furnaces. Essentially, you get a lifted flame because you want high jet injection velocity to increase mixing rates, reduce emissions, make a smaller combustor. But then you can, if you make the jet velocity too high, you can get into stability issues. So you basically need to understand the stabilisation mechanism. The stabilisation mechanism has been debated a lot over many years. There's probably hundreds of papers, I reckon, that are devoted to studying lifted flames and the stabilisation mechanism. The early theories were, and these probably apply to very large lifted heights, were this premixed flame theory, where you have sort of a wide flammable region and you have a turbulent premixed flame which propagates relative to the flow in order to stabilise the flame. Then we had critical scalar dissipation theory, where the flame simply couldn't move further upstream because the dissipation rates were too high to support a diffusion flame. That people sort of moved away from that a little bit. Although I think maybe we should probably rethink that and think about it in terms of edge flame propagation, and the fact that edge flame propagation also decreases with scalar dissipation rate. So that still may, I believe, play a role at low lifted heights. Large eddy theory is a theory in which you get the detachment of hot products from the main flame, and then, for example, folding those onto the upstream region which isn't yet burning, and that turbulent transport mechanism causes the stabilisation. Probably the most accepted theory is the edge flame theory, where you have a partially premixed flame, which, for example, was studied by Professor Suko Chong. that may have a tribrachial structure, or if the mixing gradients are too high, those branches may be collapsed into a single branch. So to study those stabilisation theories, we've done some DNS. We've done a slot jet case, so we basically have a turbulent slot jet of fuel and air coming in at the bottom, surrounded by a co-flow of cold oxidizer. We've selected the parameters to approximately match an experimentally measured round jet flame. We didn't do the round jet flame because it was a little bit more computationally expensive for us, and this was sort of at the limit of what we could do at the time. But otherwise, those parameters are matched to experiments, is why I'm saying it's laboratory scale. A fairly big domain. In terms of boundary conditions, we have outflows on the side edges here and periodic across the direction of the slot. We couldn't afford for this problem to do a detailed chemistry model, so we just did a one-step, but we did adjust it in an important way. We basically adjusted the activation energy of that one-step model so that we could get the correct dependence of the burning velocity on mixed diffraction. Notably, if you do a normal one-step model without this adjustment, you massively over-predict the flame speeds on the rich side, but if you adjust it in this way, you can get this proper fall-off towards the rich conditions and the rich flammability limit. So just in terms of overall structure of the flame, this rendering shows the vorticity magnitude in these sort of little worm, the blue-white kind of structures. And then we have product reaction rate, which is orange and red here. So you can see, just visually, you can see this flame is stabilised by an edge flame here. We see, and it's actually quite a wrinkled, sort of turbulent edge flame, so it propagates in net much faster than the local laminar flame speed velocities. We don't observe any wings of the flame. We don't observe rich branches or lean branches. We basically observe a single edge followed by a non-premixed flame. That's consistent with other measurements at this lifted height. We also observe that if we look at the sort of thickness of those little structures there, they're the order of the laminar flame thickness, which basically suggests that this is an edge flame rather than a turbulent premixed type flame. We never observed any flame, burning flames being detached and transported upstream, which essentially rules out that kind of large eddy theory of the flame stabilisation. We observed two different kinds of flame holes. You can see in this sort of downstream region that we sometimes observe extinction holes in the diffusion flame, but we also observe holes which are created at the leading edge, where a region propagates downstream, a region of unburned reactants propagates downstream, and then the flame propagates around that to create a hole which then can move further downstream. As far as we know, that hasn't been previously noted. So just looking at this in a 2D, this is the streamwise transverse direction 2D plane, similar to what you would look at in an experimental measurement. The vertical region is these blue colours here. The dashed line is the mixed diffraction, which corresponds to the maximum laminar flame speed. The solid line is the product mass fraction isocontour. So you can see there's a lot of dynamics involved here. You can see there is this sort of propagating edge flame. It sometimes is moving upstream, sometimes moving downstream, sometimes appearing to be quenched, and sometimes also just appearing in this plane to simply like appear out of nowhere, which is out of plane motion. Now you can kind of see, if you look at this very closely, it does seem to ride over large eddies. This is very obvious, like visually. It's a little bit harder to quantify, as we'll get later. And you see that it rides over the eddies and then it gets entrained into the jet, creating these sort of typical hook-like structures that have been observed in a lot of experiments. So we wanted to quantify that a little bit more, and to do that, what we've done is we've extracted information on these little red regions, which are the flame edges. We identify these in the simulation by intersection of the mixed diffraction isosurface and product mass diffraction isosurfaces, and we have a tool to extract that out, and then we can essentially find out the velocities, both the flow velocity as well as the relative motion of the flame relative to the flow on those isosurfaces. So we can get a PDF of those flame edge velocities. So this is the PDF, and this is the net velocity. Again, it's the flow plus the relative displacement. So as you can see, the mean and the median are nearly zero. So that basically demonstrates that the flame relative propagation exactly balances the oncoming flow, which essentially shows that the edge flame propagation is the stabilisation mechanism. So it's important to note that this wasn't possible in experiments because you can't, well, to experiments to date that I'm aware of, the actual propagation speed isn't measured. That's because you can't distinguish like the real propagation speed in one direction from out of plane motion of the flame, in a planar measurement. So I guess that's the first time that's been demonstrated in a turbulent flame. Another thing to note, however, is the fluctuations are very significant. They're many orders of magnitude times SL. So what are the dynamics of that fluctuation? So what we've done in kind of a long paper, but just to distill it down to one slide here, so that paper is submitted to JFM, hopefully it'll appear. You can see we've got this very complex structure. What we're doing is we're finding this little point right at the intersection of this mixture fraction and product mass fraction ice surfaces, and then we conditionally average the velocities at that location, and then this over here is a vector plot conditionally averaged on the streamwise and transverse locations. That black line there is the average stoichiometric contour. So you can see we get this sort of rotating pattern, and we hypothesize that that is due to the passage of these large coherent eddies, which is very consistent with work that's been done by Lester Su and Godfrey Mungle and co-workers based on some experimental measurements. All right, so that concludes the talk on lifted flames. Now I want to just briefly talk about the lean premixed flames. And what we've actually done here is a DNS of a burner which Marcus Ardeen actually talked about in his talk yesterday. It's a lean, high Karlovitz number premixed jet flame burner. So you basically have a lean mixture coming out of quite a small nozzle here, 1.5 millimetres, at a very high velocity. The case we did 100 metres per second, surrounded by a co-flow of a moist stoichiometric mixture. I'm sorry, this is methane air. The central jet is methane air with a phi of 0.7. In terms of the DNS, jet Reynolds number, and this is about what we can do in jet flame configurations at the moment, about 10,000. Karlovitz number is about 90, so we should expect significant disruption of the flame. The overall grid number is about 2 billion. We have about 30 species, including an NOx sub-mechanism. This cost us about 8 million hours to do this one run on this Cray XC40, just to give you an idea, about 20,000 cores. And we generated about 100 terabytes of data to look at. I have to show you the obligatory colourful fluid dynamics. This is vorticity. You can see we get the vortical structures develop in the shear layer close to the jet exit. And then when we get beyond the potential core, XOVD of sort of 10, 15-ish, we start seeing vortical structures across the jet, and then obviously it decays as we go downstream. Another colourful plot, this is our volume ending of the OH radical, so we sort of tried to make it look like a chemiluminescence, as you can see. But you can see there's a fair bit of structure there. Might not be clear on this projector, but we can also see some extinction regions close to the jet exit here. Comparisons to experiment, and this is very preliminary work. We're hoping to get more data to compare with, but velocity measurements close to the jet exit are pretty good. Looking at temperature as we go downstream, the overall agreement I think is pretty good. We over-predict the temperature a little bit, particularly towards the near the burner. That's because we haven't really accounted for heat loss to the burner. We're not quite sure how to do that in this case. So we simply just ignored that and we just focus on the downstream region. So I think the overall agreement for the temperature is actually pretty good. We also just look at just qualitative comparisons to the PLIF. So we've got experiments on the top, DNS on the bottom, OH, formaldehyde, and HCO. I think in general it's pretty good. It looks like maybe our HCO is maybe a little bit too thin. I'm not really sure. We do have this species is actually in steady state in the simulations, and that might be why it's a little thinner than the experiments. We probably need to do a better job of quantifying all this and doing direct comparisons. I think that would be an interesting point to follow up. So I'm just going to give one sort of physics result we've generated out of this. Okay, everyone here should hopefully know about the structure of premixed flames. So at high Karlovitz number, there's this question of how much this structure can really be disturbed by turbulence. And a lot of the work that's been done in DNS in this space has been this sort of isotropic turbulence cases where you don't have shear as a driving force, and it's sort of shown that I guess the flames seem to be more resilient to turbulence than you expect on the just looking at a regime diagram. So with shear, I think the situation becomes a little different. Looking first at contours, this is temperature at x over d of 4 and vorticity magnitude. So you can see at that location, it just sort of looks like a weakly wrinkled flame. You can kind of see the vortical structures are developing in the shear layer as you expect. Further downstream at x over d of 20, you can see basically this preheat zone is a mess. It's totally disrupted, and we have a lot of turbulence happening inside that, what we would normally call a flame, that preheat zone. So looking at the progress variable gradients, which you could think of as a reciprocal of the flame thickness versus the progress variable. For the laminar flame, which is the black line here, this is essentially obviously turbulence has no effect. At x over d of 4, we actually find higher gradients, which corresponds to flame thinning in this high shear region. We also saw extinction there. At x over d of 20, we see very substantial thickening, and this happens across the whole of the progress variable zone, including in the reaction zone, while at very large distances downstream, we see, again, very substantial flame thickening. So we're seeing a sort of semi-distributed type of combustion, including in the reaction zone. And as well, we see a lot of flame-flame interaction and annihilation, so that essentially these lower temperature or high fuel concentration regions simply don't exist anymore at that location. Oh, and by the way, this is consistent with what's seen in experiments as well, except that those are obviously two-dimensional. So you could have the outer plane effect, making it look thicker than what it really is, whereas those are three-dimensional. Okay, so in summary, I guess we're in this sort of era now where supercomputers are powerful enough, given really massive allocations of computing time. Got to caveat that not everyone has access to those. That we're able to do some lab-scale flames. I've given two examples. One of the lifted flames, we're showing that the edge flame propagation is the stabilisation mechanism, but this appears to be moderated by the passage of large eddies. With the high Karlovitz number lean premixed flame, we show good agreement with the experiments as far as we've measured so far, and we also show evidence of substantial flame thickening, disruption of both preheat and reaction zones. And yeah, we've got a whole heap of data here. If anyone has ideas of what we should do to analyse it, that'd be welcome. Just finally, acknowledgements, the people with the supercomputers and the people with the money. Yeah.